Zoom.
Sir?
Yes, sir.
Are both emails that you sent the same, or
Not the same.
okay? There's no difference on the second
There's
one.
no difference because I believe I sent an email. I received two email from a student that I'm not in your class. I said I'm sorry.
Oh, okay.
I do not know which email I use, but I use the one I use all the time. But anyway, I just to make sure everybody receive it again, I send it through another email to make sure that everybody receive it.
Okay.
Okay, ladies and gentlemen, are you ready? It seems there is a sunshine today, so ladies and gentlemen. As I mentioned, we finished chapter 6, 7, and 8. In chapter 7, we learn more about flow over a plate, external convection, and in chapter 8, we learn more internal. Therefore, in case of chapter 7, we look at airflow with fluid over the plate, circle, cylindrical, spherical coordinate. And in case of chapter 9 and 8, we look at the flow inside. Therefore, now we have more or less a very complete information how we can do calculation of the heat loss, heat gain, or load of air conditioning, because we have knowledge to how to do conduction. We have knowledge to look at the convective heat transfer coefficient, how to calculate. And there is still one part left that we're going to do later on, and that's our natural convection. This was forced convection. It means we have an external source that will push the fluid back up, and therefore we call it force because there's a fan, there's a pump, there is a wind, therefore that's force. And later on, we'll try to study more about the case of natural convection, how airflow around human body if there is no ventilation. And these days, these are very important about issue of COVID. Everybody mentioned about the enough ventilation, therefore more airflow inside the building is forced convection. Okay, that's the part we have some idea. Again, mentioned this is the introductory course. We give you the basic information. But if you're interested to focus, then there are some advanced courses. We call it advanced heat transfer, and therefore you can take and become more detailed analysis of the problem. We look at the one problem in chapter 7, and the solution that we had for two scenarios. The first, the heating and air velocity will start at the same point. Therefore, in that case, we're looking at airflow from here, started from here, and heating was also from x equals 0. But in some problem, in some application, usually we have a plate that air will come, and then we start heating or cooling after a certain part. Therefore, this is from a red point, we start to heat the plate. Again, we are dealing a number of the fluid. Some cases, Prandtl number is very high. Some cases, Prandtl number is low. For example, when we're dealing with liquid mercury, the Prandtl number is probably less than 0.01. Okay, therefore, liquid mercury at this temperature 250 flow with a velocity of 0.3 meters per second in parallel over 0.1 meter. Therefore, the total length of this plate is 10 centimeters. Long plate where there is an unheated starting point. Therefore, the first 5 centimeters, it's not heat transfer. Therefore, here there is no heat transfer from the plate to the fluid, but heating starts from here. Therefore, the velocity has some time to start to develop slowly. And then here we have the temperature profile, start the temperature velocity or temperature profile will start to develop. The heated section of the plate is maintained at a constant temperature of 50. Therefore, the temperature of this plate is 50. The temperature here, there is isothermal, okay? Therefore, there is no variation. Determine the local convective heat transfer coefficient at tailing edge. What will be the heat transfer coefficient at this point, okay? Convective heat transfer coefficient here, the ICH. The average convective heat transfer coefficient for the heated plate section, what would be the average, and the rate of heat transfer. And since you have, this was a week or 2 weeks ago, we had the case that you just look at here. We mentioned flat plate with unheated starting point. Here, this is starting from here at x equals 0, airflow comes, and from here the TS is start. Therefore, from the x0 to this part is unheated. Therefore, there is no heat transfer. Therefore, as you can see, the velocity profile will slowly develop, but the temperature profile will start from this point, okay, from here. We had some equation. We look at the for laminar. We can calculate the Nusselt number, assuming this heating start from this point. The usual conventional equation that we had. That was the equation that we had. Okay. If you look at it, this is local heat transfer when it starts from here. Then we make a correction to consider this phenomenon. If it's a turbulent, we have another equation. Again, this equation reflecting for turbulent. We start assuming the heating is start from here, this equation from here, and then we have this correction to make to consider this phenomena here. Okay. Therefore, here start from here, and then this is the distance. In our case, it's 5 centimeter, and here is any point from here. Okay. And then also we can also calculate the average. The average equation can be calculated based on calculating the heat transfer at any point. In this case, measure the end at x equal 10 centimeter, and then we make the correction to calculate the average heat transfer coefficient for laminar, and here is for turbulent. Okay. Therefore, these are the equations that we had it in chapter 7. Then it's the start. The heating starts sometime later on. Okay. Let's go back to this scenario, the problem that we have, and let's see how what we can do. Any question? Please ask me if you have any question. For those equations come from your textbook. The first thing we have to look at here, we have to calculate again the Reynolds number to see if it's laminar or turbulent. And in order to calculate the Reynolds number, we have to start to calculate to find out at what temperature you have to calculate the physical property. Then we go to table. Here is liquid mercury. There's a table at the end that give you all the information about the property of liquid mercury. Please do it. I cannot see you, but please take pen and pencil, open your textbook, and try to do it, at least to see which part you have some problem, because that's the whole idea of doing problem together. Otherwise, I know most of you have the solution already. You have access to that one, but the idea here is have some discussion.
Sir?
Yes, sir.
Unheated part, do we have to assume a temperature or?
Here we assume there is no heat transfer. The assume is the same as from 250.
Okay.
Okay. Therefore, we assume there is no heat transfer in this part from x equals 0 to this part, epsilon here. There is no heat transfer between the air and the fluid.
Okay.
And the only time is heat transfer starts from this one. Okay, since we have some limited time, let's do it together. The flat plate with unheated length, the thermal body layer does not begin. Please understand this part until the heated section. Okay. Okay. Therefore, until the grow here. This is at least now. Therefore, we know this is. We have velocity profile here, and then from here we have velocity profile and temperature profile. And then here we had that equation that we mentioned. These are from your textbook. Therefore, if you need them, please write it down in your note. And then we start from here. A steady operation. This is we assume the velocities remain constant. And then we assume also the temperature of the plates remain as it is. Okay, there's not changing. It's not a function of the time. Surface temperature uniform throughout the heated section, everywhere from when it starts to the end. That is everywhere the same temperature. In reality, we have to, as we mentioned, look at here. And also we assume that the physical property remain constant. Okay, again an assumption, but again depend on the scenario, on the fluid that we are discussing and so on. We have to look at case by case. Based on the information we have in our textbook, they can assume. Also, we have to look at here, this is, I'm sorry, this 5 is supposed to be here. This is a flat plate. Therefore, the critical Reynolds number changed from laminar to turbulent is around 500,000. Okay, this is 10 to the power 5. Okay, yeah, this is 10 to the power 5. Therefore, this gives us some idea how we can solve. We can assume the thermal property constant. We assume here is if it's the flow is a laminar turbulent. And again, we need the physical property. Since going back to chapter 7, mentioned we're trying to calculate the average velocity, average heat transfer coefficient, local heat transfer. We have to take the average of the temperature between fluid and the plate, because temperature up above the plate is someplace 20 to 250, close to the surface of the plate is 50. Therefore, we have a temperature gradient. Therefore, we take all the physical property at 150. Okay, and for the mercury, liquid mercury, we can go look at table A14. Okay, again, it's good to look at, familiarize yourself with the table at the end of the textbook, where the information that you can find it. It's very important, not now, not tomorrow, but in your future, because you have to go back and forth trying to find out more information about physical property of the fluid. Based on this table, we can look at and find out the conductivity. Here is 10, and this is Prandtl number and so on. Now you have the physical property, and it mentioned at the tail, at the end of the plate. Therefore, we try to see what is the flow over the plate. Is it laminar or turbulent? This is the worst case scenario at the end.
Your mic is cut off, sir.
I'm sorry. Therefore, we're trying to look at what it would be the Reynolds number at the end of the plate, because the length of the plate is 10 centimeter. He asked us to calculate the heat transfer at x equal 10 at the end. If we're trying to look at the worst case scenario, and that's the maximum length of the plate. And the maximum length of the plate is 10 centimeter. These are the velocity, these are the physical property we obtain, and therefore we can see the flow still is laminar. The flow here is laminar, at the end is laminar. It means that from the beginning to the end, the flow is laminar. Now we go back and we start to calculate the local heat transfer at x equal 10, assuming it's heated surface. Remember the equation? Now let me go back to look at the equation that you have. Look at this scenario. Therefore, now is laminar. And therefore, first we have to calculate this part. This representing local heat transfer coefficient and Nusselt number for laminar case. This is, we assume, is the plate heated from x equals 0. We have the Reynolds number, we calculated, it's laminar at x equal 10. This is local. We calculate the Prandtl number from the table. We look at here.
Sir?
Yes, sir.
What's the epsilon?
Epsilon is the length of the plate is unheated.
Oh, okay. Okay, so it's x. But wait, no.
X is from 0 to the end. X is any point. The first 5 centimeters is not heated. Therefore, this epsilon is 5 centimeters. Okay.
Okay.
That's the correction factor we have there. This is, if you look at the top here, denominator here, is the conventional Nusselt number for plate for x equals 0. And this is the correction factor in order to calculate Nusselt number at any point when the first part is unheated. Therefore, this is the equation we are going to use it, okay? Please ask me if you have any question, okay? And here, again, this is the equation that we have. And we start from here. This is the part that we have. let me go back here, and we mentioned just let me just go back. Prandtl number is less than 0.6. Therefore, we have to use a special equation because Prandtl number that doesn't apply. Therefore, here we use this equation. This is more accurate because for Prandtl number 0.6, this gives you the Nusselt number, the conventional Nusselt number, the conventional Nusselt number when the heating is started from x equals 0. Okay, it started from 0 because the Prandtl number is like standpoint, and we calculate the Nusselt number. The equation that you had that I showed it to you for the case is Prandtl number more than 0.6. Okay, this is for less than 0.6 because your Prandtl number, let me go back again, your Prandtl number is this one. When it's this one, if you go back and check the textbook, this equation will not be applied. Okay, therefore this is the conventional Nusselt number for the case that we have. This is for the, yes, sir.
We consider epsilon as 0.
Epsilon is 5 centimeters, sir.
Because it says
No,
a new
this one,
Nusselt number for epsilon equals 0.
this is the conventional Nusselt number. That means this is the case, the heating is started from here.
Okay.
This is the conventional equation that the heating started at from x equals 0.
Okay.
So this is for the case of air for Prandtl number, and the one that we show you here, if you look at your textbook, for the case when the Prandtl number is less than 0.6.
Okay.
6. This is the equation that we start, the heating is started from x equals 0. Okay.
All right.
Okay. Therefore, from here we calculate the Nusselt number. This is, we assume the heating starts from x equals 0. That's the meaning. It means the heating starts from x0. Okay. When we calculate this one, then we go back and make the correction that the heating starts after 5 centimeters. Okay. It means right here. Now, this is heating started from x equals 0. We go back and we assume now the heating is started after 5 centimeters. This is your 5 centimeter right here. And here at the point that you would like to calculate your heat transfer coefficient. And the problem mentioned calculate at the end of the plate. It means at x equals 10. Okay. Therefore, we are going to put the place a number there. We have this number from this equation right here. Epsilon is 5 centimeter. This is 10 centimeter. And put them in this equation, and we calculate Nusselt number. When you have the Nusselt number, you can calculate your heat transfer coefficient. Therefore, this is your heat transfer coefficient that you have right here. And you multiply, this is your K, conductivity. This is your Nusselt number that you assume the heating is started at x equals 0. This is your 5 centimeter, and this is your 10 centimeter. Therefore, your heat transfer coefficient at the end of the plate at x equals, this is a local heat transfer. This is the local heat transfer. At the end of the plate, at that specific point, x equals 10 centimeter, the heat transfer coefficient is 5,105. Please ask me if you have any question. Please go line by line. Ask me if you have any question, please.
What was it? 0.0468 instead of 0.05. Is it because it's actually that number in the?
This one?
No, on top.
On the top
The,
one.
the first line. Yeah.
This is the correlation that you have in case your Prandtl number is less than 0.6.
Yes.
Okay. This is applicable when it started heating from the beginning. If you want, I can go to chapter 7 and show it to you there.
No, it's okay. So 0.0468, it's a constant?
It's a constant. This
Okay.
This is an equation. This number.
Okay, yeah. All right. Perfect. Got it.
Sure. Okay, any question? The rest. 74, 73, the rest. Do you have any question? Okay, then we go here. Now we find if the problem mentioned what is the heat transfer, local heat transfer at the x equal 10. Okay, then the second part of the problem is asking to calculate the average heat transfer coefficient. Let me go back to the problem. Some of you don't remember. Here I mentioned the average convective heat transfer coefficient for heated section. Therefore, he is trying to find what is the heat transfer coefficient from 5 centimeter to 10, the average. Okay, we calculated at 10. Now we would like to calculate the average. Okay, if you look at this next slide, it mentioned the average. Use this expression. You integrate right here. You have a 10 centimeter right here. We calculated already. And we put this equation to calculate the average heat transfer coefficient. Therefore, this is the Hx we calculated at the end of the plate at this point. The program asks us to calculate the heat transfer at this point. I know at this point, I'm trying to find what is the average from here to here. If you remember, the heat transfer coefficient drop exponential right here, okay? Therefore, we calculate here. At this point is a number. We try. Now, we can use this equation, and its equation simply come by integrating the heat transfer from x equals 0, 5 to 10, okay? Therefore, we have this value, 5,000 something. We know this number, we place them, and we calculate. Okay, we calculate here. And please, if you have any question, ask. If we place in that equation, I show it to you. We calculate already this value. This value is 5,105. The rest is just the distance. We place them here. The average heat transfer is about 8,278. As you can see, the average is more than here, okay? Because I mentioned the heat transfer, if you remember, it was dropping exponentially right here, okay? At the beginning it's infinite, it's slowly dropping right here. This is the calculate.
Sir?
Yes, sir.
Can you show the slide before for 1 second? I couldn't finish the, yes,
Yeah,
1
please.
second. That's it, thank you.
Sure. And then we place it here and we calculate that the average heat transfer between x equal 5 to 10. And that's the expression that we have. Then he asks you the heat transfer, and therefore that's the heat transfer because you have the average heat transfer coefficient that you have here. You know the temperature of this plate, and you know the temperature of the air and the temperature of the plate, okay? The area that you are calculating, here is the length is 10 centimeter minus 5 because he's looking at the last part because that last part was heated. And then place in this equation and we find, since we do not know the width of the plate, it's in 1 meter. And that's why we mentioned watt per meter. Any question? Please read the problem. If you have textbook, you look at the textbook, read the problem, try to understand the problem, and if you have any question, ask. And when you are done, let me know that I go to next slide. please, when you're writing, if let me know if something is not clear, okay? Are you done?
I am. I don't know if the others are.
Yes, sir.
Good, thank you very much. Let's move. Okay, I give you 5 minutes to do this problem. Okay, bye-bye, I'm gone. You have 5 minutes, let me take the time. Okay. Okay, my microphone was off. I need some volunteer. Any suggestion?
We can. Do we have to consider taking the water from 25 to 0 and then add that, or because the question seems like we're already at 0 and then we want to keep it at 0.
Okay, this is an ice ring. The temperature of the air inside the building is 20 degrees.
Yep.
And the wall of that ice ring here is 25.
Okay.
Now the convectivity transfer coefficient between ice and the surrounding, here is ice.
Yep.
And the air here is that value. And also this is the heating. The question here is, calculate the refrigerant, how much load has to be in order to temperature here at this point 0.
So we can calculate the heat flux from the radiation, the heat flux from the convection, and then multiply by the surface area, taking into consideration that our surface is already T at 0.
Yeah.
And that
yeah. What you're mentioning here is, this is the system here. You take this control volume here, right here, and write a simple energy balance between this surface and the room air. Here you would like to keep it at 0 degree because you don't want the ice to melt. And then here, the surface of the ice are exchanging heat to the air right here and the surrounding by radiation. Could you please write that equation? Therefore, that's what we're trying to look at here is how much we have to provide the cooling here, right here, in order to keep the temperature of the ice is at 0. Therefore, at this moment, we ignored what happened inside. We're trying to see how much is the energy exchange between this ice on the floor here and the room environment. Therefore, this ice at this point exchanging the energy to the environment by convectivity transfer coefficient. We know already the H value, we know the temperature, and we know the temperature of the surface is 0. And also the surrounding, because it's a room, the wall of the room is at 25 degrees. And the exchange between the ice and this room is between 0 degree and 25 degree. Could you please write down the equation and do the calculation fast? Write the equation to see if you have a complete understanding of the problem, and also start to use your calculator because to make sure there is enough battery in the system.
Is it 96 kilowatt?
Let me try it. I have no idea. Therefore,
I multiplied the area 480 meters square times the H, the 10 times the temperature difference 0 and 20. So it's
Good.
20.
And this is by convection.
Yes.
Plus you have exchange by radiation.
Oh, yeah, true. Sorry.
Sigma A Ts minus T infinity. Okay. Therefore, here we have to consider both phenomena taking place. This is your half, and this exactly here is. Therefore, we're trying to see how much energy has been transferred from the ice. Assume that we would like to keep it at 10 degrees. Therefore, what happened here is another issue. But at this moment here, we know this surface, we would like to keep it at 0 degree. Therefore, net energy exchange with the environment, okay? As you can see, it's very easy, okay? Therefore, please read the problem, trying to make it simple. Don't make it difficult, okay? Write it down, then we go to the second part. The second part mentions how much energy needed to ice to be melted. 3 millimeter, okay? Okay, let's go back. For here, the second part mentioned how long. This is time. Please, how long will it take to melt 3 meter and 3 millimeter of ice from the surface if we do not provide, if this system is off? Okay, this system is off, is not working. How long it will take that 3 millimeter of this ice be melted? Time, okay? So we got here this value. And the second part here is the time it takes to melt 3 millimeter of ice. How are you going to solve this problem?
We have the density, we have the volume, so we can calculate the mass. Then we divide it by the time with the latent heat fusion for ice. Multiply by this, we get the energy, and then we solved it with the.
How we can calculate the time? Where the time comes in this?
Well, the time is the mass flow rate. So we have the mass, but we don't have we have the mass, but we don't have the times, but we have everything else. No?
Okay. Therefore, what you're saying, if I understood it correctly, this is the amount of the energy exchange.
Yeah, this is from the outside.
That's right, joule per second, right?
Yes.
You are correct, sir. Joule per second. And then this is energy exchange. Now, at the same time, we mentioned 3 millimeter of ice will be melted, as you put it correctly. Therefore, we calculate the mass of the 3 millimeter, and then what should we do with it?
Well, we have the, I'm not sure if that's the correct equation, but we have the latent heat of ice.
Absolutely. That's right.
So we can use the mass flow rate times this to get the energy. Well,
there's only make correction. There's no mass flow rate here. Okay, therefore there's energy flow rate here, joule per second. This is equal mass times, this has to be equal mass times the amount of the energy that needed, the times time, okay? Therefore, this is the total load of the system that we have. We calculated here, okay? This is the amount of the energy exchange. Joule per second, we multiply by time, become joule, okay? And then this amount of the energy for that period of the time. This is per second. This we multiply by this, become for that period of time, 5 minutes, 10 minutes, 20 minutes, and so on. And then we calculate the mass of the ice. This is the dimension of the ice. This is the thickness of the ice. This is the density of the ice. This becomes mass. And the time that need to change phase again, phase change, my friend, phase change from solid to liquid. Okay, write it down. If you have any question, please ask me, okay? Write it down and please ask me if you have any question. If we look at here, this is joule. Okay, joule, but this is joule per second. Therefore, we're trying to find the time. They said how much energy we have to transfer per second, watt, joule per second, in order to melt that much ice. Okay, that we find it here.
Sir?
Yes, sir.
It will work in both ways, right?
What that means both way? What that means? What is the other way? I do not know, sir. What that means, sir?
Here we say to melt 3 millimeter of ice, but we can use this as to freeze 3 millimeter of ice, provided that we give 156,300 of.
Yeah,
okay.
this is the amount of the energy exchange. Trying to understand, this is energy exchange.
Yeah.
In the surface of the ice here and the environment. Therefore, that much energy is exchanging.
Mm-hmm.
If I provide the energy here to the system by my cooling system, I can keep it frozen. If
Okay.
it's off, now is in the other way, if you would like to do that, how much energy needed to be frozen, the same thing, because this is the same amount of energy. This amount of energy needed to be transferred from solid to liquid,
okay.
and liquid to the solid. Any question, ladies and gentlemen? ask if you have any question. If anything part is not clear, ask right now. The whole idea to discuss. No? Move to next one. Yes or no? Did you finish it? Let me know when you finish writing it. I need a volunteer to mention whenever it's finished, he or she finished.
I think we're all done.
Done? Okay. Okay, let's move to next problem. Again, read the problem. The whole idea here is just for you to practice, okay? Practice. It's not exam, it's not any quiz, just practice to see how much you really know, okay? And which part of the problem is not clear that I can explain it to you. Look at here. In a pharmaceutical company, a copper pipe, conductivity of the pipe is given, the diameter is given, the thickness is given, carry liquid oxygen to a storage tank. The liquid oxygen following in the pipe has an average temperature of minus 200 degrees and a convective heat transfer coefficient of 120. The conditions surrounding the pipe has an ambient temperature of 20. Therefore, we have this pipe going to here. This is the thickness, this is insulation, okay? And here the air we have exchanging the environment, okay? The heat transfer coefficient is 20. The air is at 2 degrees and the 2 point minus 10, okay? Therefore, here is a combined heat transfer. That means you don't have to be worried about the radiation, okay? Determine the thickness of the insulation. How much insulation I have to put to avoid condensation on the other surface, okay? At this temperature, the dew point is minus the 10 degree. How can we solve this problem? Read it again, try to understand, okay? Don't be shy. If you have any question, ask. Because in order to be able to solve the problem, you have to really understand what is going on.
We consider one direction
It is one dimensional.
transfer,
Yeah.
one dimensional. We add the resistance from the pipe and the insulation, but the insulation is unknown, so that we don't attain 10 degree from the 200, from the minus 200.
Write down the equation to see what is given to you and what is unknown.
Okay.
Because I can, as you mentioned, I know that the temperature outside, I know the temperature of the ambient, but the problem here is the thickness is not given, thickness of insulation. But also, if draw the thermal diagram, the resistance from pipe to the outside to see what is given, what is unknown. And based on the information is given, mentioned the dew point 10 degree, how can I use that temperature? Therefore, please first trying to draw.
So so the 10 degree, we can use it at as our T surface maximum or minimum, because we don't want it to reach below this.
Absolutely. Therefore, if you plot your resistance, you have the temperature here. You have convective heat transfer to here. You have conduction to this wall. and conduction through the insulation. And here, as mentioned, this is the worst case scenario. You don't want the temperature to go below 10, okay? You don't want to here because you go below this one, you have condensation. Therefore, from here, you assume the 10 degree, then you have the ambient temperature. Therefore, from here to here, you know all the information. The temperature is 20 degree, the temperature is 10, your heat transfer coefficient here. But you do not know the surface area because you do not know the thickness here, okay? Therefore, write all the information from here to here and to see how we can solve the problem. What I know here, from here outside, I have all the information. I have the temperature of the air, I know the surface temperature, but I do not know this one. I do not know the radius here, from here to here. Because in order to calculate the area here, I have to know the thickness of the insulation. Write it down to see where is the challenge, please. But also keep in mind, please keep in mind, this is a cylindrical coordinate. Okay, this is a cylindrical coordinate. Keep in mind, okay? Therefore, when you calculate the resistance, you have to remember how to do that. Okay, 2 minutes, please do it. What is the thickness? What is the thickness? Okay, we draw the thermal diagram and we wrote the energy as center of the pipe to the outside. And if you do that, we have this one right here, okay? This is energy between inside and outside, okay? From here to outside, the temperature difference between inside and outside. This is one, we have outside combined radiation and so on. We have conduction through the insulation, conduction to the wall, and convection inside the pipe. This is simply if we add them together because they are in series together, and if we add them together, become this one, TS surface to outside combined. Do you have any question about this equation? Therefore, this is the resistance from outside to the surface of the pipe. Here, mentioned combined heat transfer here. This is conduction to resist to insulation. This is conduction to the thickness of the pipe. And this is the convection inside the pipe, because the liquid nitrogen is moving and the heat transfer coefficient has been given to us. Since it's steady state, this is equal to energy transfer from outside to outside. T outside minus the temperature of the surface divided by the resistance in this part. Yes, sir. Yes, sir. I'm sorry.
Oh, no, you had just answered. So I just answered the question. So I thought you just changed T infinity I to TS, but it's just a different heat flux.
That's right. This is the energy come from here to outside, from
the surface
is equal to surface to here. That's exactly the point. Because it's a steady state. Okay. Any question, please? Therefore, this is simple energy. We wrote a steady state scenario, and we mentioned from inside to outside is equal from outside here. Yes, sir.
The right part of the equation is from the surface to the surrounding air.
That's correct. This is outside temperature. This is temperature of outside. It is 20 degrees. This is surface temperature. That if you like to put 10, and this is the.
So all combined is just H, right?
That's right. This is the only part. Because you mentioned that's right. Okay.
Okay. And the other one is from the center of the tube, the pipe, to the surface of the pipe.
This is here is.
Oh, to the surrounding. Okay.
This is for insulation, resistance to insulation.
Yeah.
This is
from copper
conduction.
And
here convection here. That's correct.
Okay.
Now we have to go back and define each resistance. Again, keep in mind, this is a cylindrical coordinate. Okay. Keep in mind this is, therefore, if I remember it correctly, this become like this. This is outside 1/h. This is through the insulation. That was log of this over this. Therefore, this is the radius that we have. Okay, here and here. This one, 1, 2, right here, from here to here. Because here the radius is 3. This the radius is 2. This is through the thickness of the copper, the R1, R2, or D1 or D2, right here. And here again, convective heat transfer to the inside the pipe. Okay. Therefore, we have to keep in mind, I put A. You have to make sure this A is different from this A. I have to remember. This is the area for the interior part right here, this part. This is area outside. Therefore, you have please put A0 and AI. That we keep in mind. This is area, convective heat transfer from outside the pipe. This is convective heat transfer right here, this part for inside the pipe. Therefore, this is AO outside, AI, and AO. Is this equation clear to you, ladies and gentlemen? Don't be shy, ask any question you may have. Good. Therefore, now we look at this equation, we have all the number. The only thing you have to remember, this is exterior surface. This is outside. And this here is AI. We go back. Area for outside is PD times L. Okay, this is perimeter times the length. This is D1L, this one, and this one. Okay, please put A0 outside here, and this one is interior. Okay, and since this is we know all the information, if we substitute here to see what What is the unknown in this equation? What is the unknown in this equation?
Some D3.
D3, excellent. Therefore, excellent. The only unknown is D3 because we know the surface temperature, because we mentioned if should not be below 10, okay? If you substitute, your equation become like this. Again, this is just rewriting the equation. This is this one, this is this one, right here, and all the equation, and you can calculate D3 from this part, okay? And then, okay, write it down. If you have any question, ask, please. Please let me know when you're done. Can I move? Can I move the
Yes.
go to next? Okay, please let me know because I have no idea. And therefore, the only thing is D3, and you write it down and put this number, and D3 become like this, okay? For now, you have the diameter of this one, okay? Is it the total diameter? Yes, sir.
How do we get the ln when we do the?
Yeah, because
I
this
forgot.
is a little bit trial and ln here, since you do not know this one, you have to write this equation here because this is known value, this known, and for this term become equal one number. And you have to do the try and error because you have this one and this one. This is not going to be your exam question because you have two unknown here, right here, ln
Okay.
as well. Okay. But assume
But
that
what I'm saying in the first equation before, when we get the ln d3 over d2, I forgot. I know it's for the resistance of it, and it's from having a circular shape, right?
that's right. When it's cylindrical,
Okay.
that's right. Okay.
All right.
If you become spherical, you have another D3 somewhere around here. Okay.
Okay. All right.
Therefore, to calculate this one, since you know D2, you minus subtract D3, and that they gave you the thickness of the pipe. Okay. Since you know already what is D2, here is 25, and your D3 become 30. Therefore, this shows the thickness between these two. Okay. You know the diameter here, you know the diameter here, you subtract them, and you find out your thickness should be more than 0.29. Okay. Any question, please? And why it is divided by 2?
Because the diameter includes the thickness on both sides.
Very good. Excellent. Excellent. Okay. Therefore, you have some idea how to solve this problem. Okay. Any question, please? Please, when you finish, let me know that I can go to the next one.
So problem like this with trial and error, you said we don't have this in the midterm.
No, sir. No, sir.
Take too long. Okay.
No, it's, you can do it easily, but that's by program computer. But that's no, that's not the focus. It's not mathematics or the idea here. The exam is trying to make sure that you have the minimum understanding of the course.
All right. Thanks.
Okay, may I move to next one?
Yes.
Thank you, dear. Let's move to next one. Okay, read it and try to do it. I'm going for a walk. I will come back in half an hour. Therefore, we're trying to find the temperature distribution in the spoon. The dimension is given, 18 centimeter. And the temperature of the water is given, the temperature of the ambient and kitchen has been given, the physical property of the material has been given, everything has been given. Therefore, we have to write a set of finite difference equation for each node, okay? If you look at here, I'm sorry, I have all the solution here. I'm sorry, I forgot to change it, okay? Just pay attention, then you can have time, okay? Therefore, this is the spoon that you have. This part is in the water, mention the temperature. And here is going out. We have conduction through here. And therefore, mention to discretize every 3 centimeter. Therefore, we have the length. We can just find out how many nodes we have. We have 7 nodes here. Node 0 here, node 1, 2, and so on, all the way to at the end. Okay, therefore here from 0 that we have at this one, the temperature of the boiling water is 100 degrees. Therefore you write the node from 1, 2, 3, 4, 5, 6, 7, and so on. Okay, they have 6 nodes that you have. If you look at from one, yes, dear.
Wasn't 18 centimeters just the part of the handle that was outside of the water?
No, it's 18 centimeters is the total.
Okay, I think I read extends from
Let me
the
see.
surface. Maybe that's my mistake.
Let me see. Let me look.
I read it as just the handle as well.
Let me see. The handle of the, okay, that's at 18 centimeters a handle right there. Therefore, here is the water, but here the way it did it is 7 now. Okay, therefore we can go back and the same thing we can assume here is from, you have to mark, change it differently, okay? Therefore we have a spoon here, 18 centimeter, and they have all the one in the water, because the problem here is, if you go back here, mention the boiling water and the handle, this one 18 centimeters, this one the convective heat transfer with the ambient air, that's correct. Therefore the whole, the figure is wrong, okay? Sorry, that's you're correct. Therefore we have a spoon from here to outside is 18, the rest, whatever is in the water is at 100 degrees, okay? Therefore from the water, if you assume this is the water here, from here to here is all of them are 0, okay? The spoon here is 0, and from here is node number 1, we start going up all the way to here. Okay, please modify this figure, okay? Mistake, okay? But therefore this is still, we have 7 point from the surface of the water, then all the way to here. The rest here is at boiling point. The rest here, the boiling point is 0 degree, okay? If you look at, if you draw it here nicely here, you can see node number 1 all the way to node number 5 are interior node. Therefore, what that means, it means the equation for this one is the same as here, because this one conducting to this node, this one conducting to this node, and convecting to outside. The same thing for 4, the same thing for 3, and so on, except this node outside at the end to have different. Therefore, we assume the temperature here is all of them is 100 degree until this point, and from here the temperature is changing because it's convecting heat to room, the kitchen environment, okay? Therefore, there was one point here is trying to make, I would like to make sure that you understand here is, this is equation for all the nodes from node number 1. Again, this figure is drawn. Node number 1, we assume here is at this point, okay, up there. The rest, if it's this is the surface of the water, the temperature inside is there. Therefore, we can write this equation for every node. We assume this is node number m. This become m minus 1. This become m plus 1. Okay. In general, if we're writing a general equation for interior node, therefore 5, 4, and all of them will consist interior node, okay? That means you have conduction to this node, conduction to this node, and convection to outside. If you look at here, conduction to this node, conduction to this node, and convection to outside. Therefore, this equation will apply from m equal 1 all the way to m equal 5. All of them the same. You have conduction from this node. You have conduction from this node, 5. You have convective heat transfer to outside. Here, this is the outside here. And you also to consider radiation outside. Therefore, this equation can be applied for right now. Any question, please? Please modify this figure. Therefore, the node number is from surface up there, okay? We assume here this is node 0, that at 100 degree. Any question, please?
Is heated density of the air?
Say it again, please.
What's P in the formula? The letter P.
P is the perimeter.
Okay.
This is your spoon, okay? And here the conduction comes from here. This is the perimeter of here. This, okay? A plus B times 2. If we assume rectangular, okay? Therefore, this is the cross-section area. This is a cross-section area. This is the perimeter of that cross-section area times delta x, the length, okay? The delta x. Okay, therefore, if you modify this equation, become like this, okay? We will discuss about the solution later, okay? Therefore, this applies for all interior equation that you have. And the last one, if I look at here, is we are talking node number 6. Node number 6, from here to here is delta x. From here to here is delta x. We assume from the bottom here is give you convection to outside, convection to outside, convection to outside, okay? Whenever you finish, let me know that I can go to the next slide. Any question about this equation?
Yes, for me, yeah, myself, I'm done. I don't know.
Okay, we take you as an example. We move to next slide. The rest, are you finished, please?
Yes.
Yes, sir.
Good. Therefore, this equation can be applied from 1 to 5. The only left one is number 6. And number 6 is, you can write here, this is conduction from 5 to 6. This is convection from the top of the spoon to ambient. This is radiation to that from the rest, okay? Look at here.
Should
This-
it be 0.7, not 6?
0.7.
Node number 7,
No. This is last one is node number 6.
not 7?
No, we have only 6 nodes. We divided to 7 parts from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4, 5 to 6, okay? Because the first node is not 0, and that's we assume the temperature is constant.
Because in the last slide, the previous slide, you said equation to find how many nodes.
Number of section.
M equal L over delta X plus 1.
Yeah.
Yeah, but if you begin by 0, if you start by 0, you're going to get to 6 instead of 7.
Okay, thanks.
Okay. And then here, look at here, there's 2 parts. This is the part and this part, okay? This is from the top and this is from the side. Look at here, the node 6, it has is rectangular. There is something from the top to outside, and there is something from the sides, okay? Therefore, convection from here to here, convection here, and also this is a rectangular, some convection from the top, okay? Therefore, this is the cross-section area. Therefore, you can look at here, this A is the same as this A, plus something from the side of the spoon, okay? From side of the spoon. The same thing for radiation. Radiation from the top part and radiation from the side part, okay? Therefore, here we write it down and look. But of course, you cannot solve it here because you have the temperature to power 6 to power 4. In all of your previous equation, you have temperature to power 4. How you're going to solve this one? If you're doing programming, because you have temperature power here, m, these are unknown, but this one is also to power 4. This one is power 4, and also all of the equation have to power 4. This is not it's not an exam, but just for curiosity.
We have to do trial and error again until we find something fits.
One way is trial and error. And if you remember in building science, we normalize this equation. If we can mention this is also is HR minus times TS, T surrounding minus T6. We were defining radiation heat transfer is equal HR, radiative heat transfer coefficient, times area times that one. And we can define what is HR. Anyway, we can discuss it later on, okay? But the one way is based on trial and error, but this becomes very difficult because you have 6 unknown. But you can sort of define an HR, a value, trying to calculate the temperature and come back and verify if your assumption is correct or not. But again, this we're going to discuss it later on in radiation chapter. Therefore, these are a number problem is not exactly exam question, but the question forcing you to understand the fundamental, understanding the basic. The exam is going to be at the same level your assignment. The idea here, I want to make sure that you have the minimum understanding of this course, okay? Therefore, do the problem. If you have not looked at the assignment yet, try to do the assignment. The number is not important, how many problems you do. Do 2 problems, 3 problems, but do it all the way to the end. Put your solution on the paper to make sure that you really understand. Don't look at the solution and say, well, I know it is easy. Yes, you know it because you see the solution. In the exam, you don't have the solution. Read it, put your solution on the paper to see what exactly is the procedure to do the problem, solve it, get the answer, then look at the solution. If you have the same solution, go have a coffee. But if it's not, find out where you made mistake, because you have to write down on the paper, you see your mistake, that you do not make that mistake again. Anyway, ladies and gentlemen, I'm here for the next 5, 10 minutes, 15 minutes. Before the sunset, I would like to go for a 5, 10 minutes walk. If you have any question, please do ask me. I'm here.
Sir, I just had a question regarding the midterm. So we have to connect to a Zoom meeting as well as the proctoring.
Read those instructions that I sent it to you. That's all information I have. But you have
Because
to.
you sent 2 emails regarding the midterm. The first one talked about a Zoom meeting.
The same. No, the same. Both of them are the same. I just forwarded the next one. Both of them are the same.
So is there a Zoom meeting or no?
Both of them is the thing. The exam, I believe, call is going to be done through the Zoom. My understanding it is. Am I correct or not? I do not know in experience.
Well, from what is written on there, like we are being filmed and recorded.
Yes.
And like it's not Zoom. We have to download a plugin. And did you check what is the warning when you upload that plugin? It's a bit.
Therefore,
I invite you to go and read it because I've been doing research since like 2-3 days, and it has access to your whole computer. It's a bit
Absolutely, absolutely. Yes, yes, yes.
But
the
what
learner-
if we are working in a like a consulting and like everybody is working remote right now? How do we
and
make sure we are reliable with the information, that the confidential information?
Well, I mean, they question the learner from the mistake from the last term, okay? Therefore, they're trying to take extreme scenario. You know better than me.
Okay, but do you have any like
I don't have any.
way? Because I've been looking for like 2-3 days, and like I cannot confirm to my company that the confidential information
What confidential
will be
information?
protected by downloading that app. So
What's the confidential information? There's nothing. They only would like to look at you. That's all.
no, it has access. I can send you what is exactly written.
Don't send it to me because I'm more naive than you, okay? But they are going to
But
contact.
I feel like you should know because you're the one that decide that. We
I will-
follow you.
Exactly.
So
I
do you know what that means? It's a bit.
I have my suggestion here. As you read your email, they mentioned they will send it to you 1 or 2 days before the exam, but you can ask them any question that they would like to do that, okay? And you can, that I believe in that email, there are some information.
Yes, I've been looking at that like since 2-3 days.
Therefore, that you can contact them and get more information. I will try again. I have the same problem as you. I have to get it from somebody else. But your camera has to be on. Therefore, they would like to have make sure everything done properly.
I understand all that, but I don't understand like how having access to my whole computer and all the information in there add up to the integrity of that class, because I want my degree worth something and I want to have like a good integrity of the class, and I understand it's for that, but I don't understand how putting my data.
I don't think so. They are going to come to check your computer.
But what is written black and white is that they have access to pretty like everything, and there's no like time frame for that. So it's a bit like I don't understand why there's not like clear information, and what is written on Cole and what is written on the Proctorio website doesn't jive. So I'm still looking at like an insurance, because if I'm working in a company, I want to be able to tell them that yes, my computer is safe.
Okay, the best thing here, contact university, contact the chair of the department, contact the undergraduate coordinator. Probably they are more informed and educated than me. Probably they can provide you. Mentioned in general, because you don't mention about this specific course. You mentioned this is one.
No, it's just the whole like
your question correct. My point here is your question correct. I absolutely agree with you. I cannot give you the definite answer because myself I'm absolutely illiterate in that aspect.
Okay. Well, I invite you to go and check yourself as well. No, because I feel like it's something that nowadays we are all facing, and like
believe it or not, I'm sitting from the front of the computer from 6 o'clock in the morning until 9 o'clock in the night because we are dealing with a lot of this type of case.
Yeah, it's the same.
We have ordered some equipment for my experiment 6 months ago. We have not derived, we have not received it, and we have a lot of problems. But
yeah, nowadays it's like a constant problem. Everybody is doing.
No, I'm not complaining. But for you, in order to make sure you have the correct and accurate information, I suggest to contact the chair of the program or undergraduate coordinator. Probably they have better information than me. And that way, but I sent already an email. I already sent an email. I asked them, could you provide more detailed information for the student? But as you said, they're saying this is, go to this website, go to this website, go to this website. And rather than me going to each website, trying to explain to you, your English is better than mine. Probably you have much better understanding of those statements than me.
I feel we're in the same boat, but okay.
Okay, your English is speaking, I'm not, okay? Well, this is my second language. Therefore, it's better check the website to see what exactly on the website, rather than my interpretation of those statements. But you have a right question, you are valid, but unfortunately, I cannot give you like 100% complete information answer because some information is also not clear to me. No.
While reading both emails, I still don't understand if we're being monitored through Zoom or through Proctorio.
Proctorio.
Proctorio? Okay, so there's no Zoom.
Again, don't quote me. They are going to send you information in the next 2 days, an email to you directly, and to tell you exactly what's going on. what they need, you have to have a camera. They should have a complete view of your surrounding. Either way, both of them, they need the camera to check that they learn from the mistake, my friend. You know what do I mean, right?
Yeah, I have no problem. I just want to make sure I have the proper stuff before the exam.
That's my. I believe if you read the email again, the same one is the same. Both email are the same. I cut and paste and send it to you. Both email are absolutely the same. They are not two different email. If you receive from me, is the same email. Okay, the same email. But I send it twice because some student wrote back to me and said, I have not taken your course. I said, I'm sorry. Therefore, to make sure, I send it again to all of you. Read it, and I believe you read it again carefully. Mention they're going to send you email 1 day or 2 days before the exam to provide you more information, and therefore you can ask them more questions. And I believe also you can ask somebody else that I'm sure this is not the first exam you're taking, but I'm sure you have seen it before.
No, I personally have never done a proctoral exam.
Me neither. All the teacher are avoiding, and some are watching us via Zoom, but it's really the teacher that is on Zoom, so it's different.
This is also my first one.
Yeah, same.
Yeah, me
I
too.
think
It's the
this is
same. It's the
the
same.
first one.
That's why we have questions. Like, it's new thing for us. So.
As I said, all the information I had, I forwarded to you, but I also asked them more specific question. I'm waiting to hear from them. But if you read that email, I sent it to you. They mentioned they're going to be in contact with you in 2 days or before exam. Therefore, you should get an email anytime these days from you. It will provide you more information. And I'm not involved in exam protector. It will be done by invigilator. There are some invigilator that are going to break down to you 2, 3, 4, 5 groups, and invigilator, each one is going to be responsible for one section. Because I don't want to have anything with it. Okay then. Anyway, just study, and I will be in contact with you in the next few days.
Thank you, sir.
This is the information I have. I cannot give you any other information because I do not know exactly how it's going to be done. All the best. If you have any question, please do not hesitate to contact me or TA and so on. Hopefully everything will go well.
Thank you, sir.
Thank you there. Bye-bye.